Welcome back, everyone. Today we're going to be looking at our chapter 4 of advanced functions, and today we're going to be looking at sketching the graphs, and we're going to looking at some transformations to the parent functions that were introduced last class. Let's go ahead and get started. So the same transformations have been applied to 6 different parent functions as shown below. So we can look at this annotations and we can see that all of them are the same transformation. So this introduces us to our generic form, where when we have the transformation, we no longer write it independently. So for example, let's take y equals x squared. We don't write y equals, we no longer write y equals 2, and then we see, oh, it's 0.5, so 0.5 x minus 1 squared plus 3. We no longer write it like this. Instead we write it generalized, in a generalized form. We're talking about functions instead of specific functions. So we observe these different functions, and we have. So let's go ahead and define. Let's look at the transformations. So obviously we can see that these transformations affect these graphs all different. They're different by a bit. So let's go ahead and write down what these transformations are. So we can see it's a horizontal stretch by a factor of 2. To write this. And then while we have this horizontal stretch, we also have while we have this vertical stretch by a factor of 2, we also have a horizontal stretch by a factor of 1 over 0.5, which is also 2. And then we are moving negative x minus 1, so we're moving, translating 1 unit to the right, while we're also having translating 3 units upwards. So these are the transformations, and we basically apply them to each of the functions. And then we can go ahead and move on to the next part, where we get onto some examples. Let's go ahead and do that. State the function that would result from vertically compressing f of x by a factor of 1 over 2, and then translating the graph 5 units to the right. So as we talked about, we're no longer writing specific forms, like let's say y equals, we're no longer writing like this, y equals 1 over 2 x squared. Instead, we're writing it generalized. So instead of putting x squared there, we just put f of x, right? So state the function that will result from vertically compressing the y equal to f of x by a factor of 1 over 2, and then translating the graph 5 units to the right. So this is already the compression part. If you can tell, this is the compression part. We have already compressed it by a factor of 1 over 2. Now notice the 1 over 2 is on the outside of this. Now when we talk about translating 5 units to the right or left, we're talking about a horizontal translation. So when we have a horizontal translation, it goes inside of the f of x instead of outside. So we will have 1 over 2 f of, and then we're translating 5 units to the right. It's basically x minus 5. So x minus 5. And that is our answer. And this is a generalized form. By that I mean you can sub any function in. So let's say y equals to f of x, and so y equals to f of x, while it's equal to square root of x. And then we could just basically sub this in, and y would now equal to 1 over 2 square root x minus 5. This is a generalizing form. We can input any functions we want. Let's go ahead and move on to the next example. Wow. I killed it. Okay, example 2. Use transformations to help you describe the characteristics of the transfer function y equals 3 square root x minus 2. Why is it shifting? Okay, so first, when we have a function like this, we will usually get started by writing out our general form, which I will actually keep on the screen. Y equals AF K, this should be a square bracket, X minus D plus C. Or you could see other forms. It depends on what your teacher likes to use. There could be a X minus P plus Q. I use that one, but both of these are fine. So in this one I'll highlight, actually I won't highlight this. So in this one we have parameters. We have changeable variables that we could input. They're not variables, they're factors that we put in. The parameters K and D affect the x coordinates of each point on the parent function. Meanwhile, uh, A and C affect the y coordinates of each point on the parent function. So basically, we can write, based on these transformations, we can write out what the chords of each resulting function is. So for example, the original parent function had chords of x and y, obviously, and then after the transformation, we would have x over k, because that's how k works, plus d, and then we will have ay plus c. And based on whatever your k, d, a, c values are, you could just plug it in, and we could get this parameter function that we can use to find every point. So let's now look at the equation, and this I'm gonna keep it here because this is helpful. So yeah, I'm gonna keep it up here while I'm gonna move this because this is helpful. Ooh. Okay, let's go ahead and look at this function. 3 square root x minus 2, that's pretty simple. So we could see that this 3 is outside and we only have a and c values. So this is an a value. This right here, that's an a value. And this right here, it's a c value. So what that tells us is that we will have a vertical stretch by a factor of 3 and a vertical translation 2 units downwards. That's all we can say. And then we could also summarize that a equals 3 and c equals -2, but that's not important. Alright, let's move on to the next. So question number 3, example number 3. Reasoning about the characteristics of a transform function. Now we're talking about trig functions, and now our k values have a different meaning. So graphing the function f of x equals to cos x, and the transform function y equals to 2f of 3x, where 0 degrees is smaller than x, so we bounded the x within 360 degrees. State the impact of the transformations on the domain, range, intervals of increase and decrease, and turning points of the transform function. So when we're talking about trig functions, our k value has different meaning, or our k value has different meaning. So instead of k value impacting x directly, we're actually changing our period. So let's go ahead and talk about this. So first, we want to write out the general function. So we know that a equals to 3, a equals to 2, and then we have k equals to 3. That's pretty clear. So x, y now becomes x 1 over 3x, because we're doing x over k, so x over 3 or 1 over 3x, doesn't matter, and then 2y. And now based on this, we could graph an entire transform function. So let's go ahead and have some key values. So let's do some key points on the original graph. So let's have 0 degrees and 1. So our cos of 0 is 1. What does that become? That becomes 0 and 2. We're just applying. So 0 divided by 3 is 0, and 1 times 2 is 2. Now let's see what other key points. So 90 degrees and cos of 90 is 0. And then now what we have is 30, and 0 times 0 is still 0. So 30 degrees we'll have 0. And then 180 degrees we'll have -1. And now 180 divided by 3, that's just 60. And then while -1 times 2 is -2. And then 270, that's 0 again. And then now we will have 90 and then 0. And then finally we'll have 360 and 1, which becomes 120 and 2. So what do we do with this entire... So you can go ahead and graph this function out on Desmos and check out what it does. But basically what I'm going to tell you is that within our specified domain, the transfer function will increase and decrease on a certain interval. So actually, let me just go ahead and give you the graph of the resulting function relative to the original one. So right here, where did it go? Okay, right here, this is our final resulting graph compared to our original one. So the blue one is annotated f of x equals cos x. That's our original one, and this is our transform one. So notice the 2 will increase our range. So from going from 1 to -1, we now go from 2 to -2. That's pretty good. And our period becomes only 120 degrees. So how do we find the period? It was just basically 360 divided by k. So 360 divided by 3 equals 120. Makes sense. That's correct. Let's go ahead and talk about the intervals of increase. So intervals of increase, we're looking at intervals of increase. Intervals of increase from 60 to 120 degrees, from 180 to 240 degrees, and from 300 to 360 degrees. Intervals on decrease are 0 to 60, 120 to 180, and then 240 to 300. The transform function has the turning points of here, so 0, 2, 60, -2, 122, 180, -2, 242, 300, -2, 362. Well, this doesn't really count as a turning point because our function is cut off. Everything from the right is gone. So yeah. So, and we also have to talk about the domain. So domain doesn't change. So the domain consists of every real number and then our x is also bounded. So from 0 degrees to 360 degrees. But our domain has changed. The vertical stretch has changed the range from hold on. So the range has changed from YER. So from y equals to all real numbers. From y equals all real number, such that -1 is smaller or equal to y is smaller than or equal to 1. It actually changed to y is all real numbers, but -2 is smaller than y is smaller than 2. So this domain, because we had the transformation of the vertical transformation of a equals 2, so this entire transformation, because it's a y value, it takes the transformation as well, and now our entire range got multiplied by 2. Hope that makes sense, and let's go ahead and move on to our very last example. So example 4. Now all of these are in the textbook, so you could go ahead and look it back. If you have something that you don't really understand, you could always check in on it again. So let's go ahead and look at this. Reasoning about the order of transformation. So now we're talking about which one, and we also got every possible transformation on this. So we have the A value, the K value, the P and the Q value, or whatever you call them. But yeah, we have everything. So describe the order in which you apply the transformation defined by y equals -2 f of 3's bracket x plus 1 bracket minus 4 to the function f of x equals to square root of x. Then state the impact of the transformations on domain, range, intervals of increase, decrease, and in behaviors of the transformed function. Let's go ahead and look at this. This is a very interesting function. So without getting too stressful, let's go ahead and name what these transformation variables are. So a equals to -2, and then what other variables we use? K equals to 3, d equals to -1, because remember we are doing x minus d, but now it's x plus 1. So x minus what will give you plus 1? So x minus -1 will give you plus 1. And then c equals to -4. Alright, so let's look at the transformation, and we're going to use our, transformed functions. Let's go ahead and see x and y. So xy after the transformation will now become x over k. So we have 1 over 3x again, and then we will have -2y. Oh wait, no, yeah, we'll have that, and then we'll also have -1, and then here we will have -4. So this is the entire transformation. And as we learn in grade 11 and grade 10, we will always do the stretch, compression, and the reflection first. And then after that, we'll get to all of the translations. So when we first do the reflections and everything, let's go ahead and get rid of these translations. So let's get rid of these translations. So after the reflection and the stretch, the compressions, this was what we have. Let's go ahead and enter some key points of the square root function. So what does the square root function have? Key point 0, 0, 1, 1, and then 4, 2, so 9, 3, 16, 4, all of these perfect squares. So let's go ahead and see. So 0, 0 is going to give us 0 and 0 again. And then we'll have 1, 1, which will go ahead and give us 1 over 3 and -2. And then we'll have 4, 2, which will go ahead and give us 4 over 3 and -4. Alright, so we're seeing some transformations already. And then finally, let's do 9, 3. So 4 key points should be more than enough. And then this 9 divided by 3 will just become 3. And then 3 times -2, so -6. So we'll have all of these done. So the multiplication must be done before addition, right? Because these are all multiplication. So no matter what translation we add, -2, -3, -4, whatever, it will always be done after the multiplication. So applying a horizontal or vertical compression stretch by any factor, these reflections, this must be done before any translations. These will involve multiplying the x and y coordinates. So these must be done before any translations. And it will make your life so much easier. So we have all of these. These are above are the points after stretch / compression. Stretch. How do you spell? Okay. Stretch / compression / reflection. And now we're going to go ahead and add in the translation. So 1 over 3x will actually now have -1 behind it because that's the d value. And -2y will now -4 because that's the c value. So let's go ahead and do this. So 0, 0 became 0, 0 will now become -1, -4. Right? Makes sense. And then 1 over 3, -2 will now become -2 over 3 and -6, right? Makes sense. We're only moving it. So 4 over 3, -4 will now become 1 over 3 and then -8. And then 3, -6 will now become 2 and -10. Right? It's all making sense. It's just math. And then these are above are the points after both stretches and translations. Right? So these are what we have. So now let's go ahead and look at the final everything done transformed function. So the textbook is really nice. They gave us 2 different versions of that at the same time. So we have green, which is the original function. We have red, which is everything after the compression and stretch and reflection. And finally, we have all of these horizontal, vertical movements. That's translation. So we can see that the real big change comes really honestly from the compression and the stretch and the reflection. See, this from green to red, that's a huge transition. And from red to blue, it's just really moving places. Not too big of a deal. Most people make mistakes on the stretches. They fail to analyze some of the AKDC values. But usually from red to blue, it's a really simple crossing. So now let's go ahead and talk about the domain range intervals of increase, decrease, and behaviors. So originally, the function increased, but now it decreased. The original function was always increasing. It was monotonic. It was keep on increasing, but now it's a decreasing function, and it decreases from decrease from the interval. Wow, why doesn't my pen work? Okay, so it decreases from the interval of -1 all the way to infinity. And now infinite this should be a square bracket because that's part of the value. And now infinity. So this is decrease. Wow, it doesn't work. My pen suck. So decrease on the following values. Decrease on this interval. And then let's look at the transform in behaviors. So as x approaches -1, y approaches -4. Originally, the function was as x approaches 0, y approaches 0. And as x approaches infinity, y approaches -infinity. So let's also talk about the domain and range. The domain is pretty much unchanged except we moved it a little bit. So from x is all real numbers and x has to be greater or equal to 0, we have this this horizontal translation. Now it becomes, wow, now what? Now this becomes, now this will just straight up become x and now x has to be greater or equal to -1. So we move this, and because we had 0 originally, so any of the k value doesn't work at all. So all we have to do is just apply the horizontal translation. Now let's look at the domain. The domain used to be pretty simple as well. It's pretty much just y is all real number and that y is greater or equal to 0, right? This is pretty straightforward. And because y equals to originally this is just 0, when we apply the vertical transformation, so when we multiply by -2, it's just still 0, or it's -0. It doesn't really work. So now after the vertical translation of y equals to -4, so our range has changed from y is greater or equal to 0 to y is greater or equal to -4. Right? It's pretty straightforward. And with that done, that is everything that we have to conclude for all the examples that we have to conclude. So let's go ahead and look at the final summary and the key ideas of this lessons. Should be on the right. Yeah, let me paste it in. Let me just do that. Yeah. So the key idea is that transformations on a function y equals af k x minus d plus c must be performed in a particular order. The horizontal, vertical stretches, compressions, including any reflections, must be performed before the translations. And every point on the graph of the parent function are changed as follows. Right here, so we write our general form. And when using transformations to graph, we can apply a and k together and then c and d together to get the desired graph in the fewest amount of steps. And that sums up our entire lesson. Oh, actually, no, there's a little extra part that I always forget. The need to know part. This part is not as important, but we need to know, what do we need to know to kind of solve the problem? We need to know the value of a. The value of a determines whether there's a vertical stretch or compression or a reflection. So when the absolute value, so we no longer look at the signs. When the absolute value is greater than 1, the graph is getting vertically stretched by a factor of the absolute value of a. When 0 is less than the absolute value of a is less than 1, the graph is getting compressed. So we're using absolute value here, and absolute value can't be negative. So when a is negative, this is no longer the absolute value. The graph is reflected with the x-axis. So we can see over here, the green is originally in the top. Now we reflect it. Let's say we have a mirror. This would go ahead and come onto the bottom, something like that. Okay, that didn't draw well, but it's okay. It doesn't matter. So yeah, you get the point. And the value of k determines whether there's a horizontal stretch or compression. So when absolute value k is greater than 1, the graph is getting compressed, because when we have the k values, it's always x over k, right? It's always x over k. So a value of k that's greater than 1 would actually be a fraction for x. And then when 0 is less than k less than 1, the graph is getting stretched horizontally because we're dividing by a fraction. So let's say 1 over 1 over 3. Instead of giving us another fraction, it actually just gives us 3. You should know that by now. When k is less than 0, the graph is reflected in the y-axis. Let's see if we have an example. Nope, we don't, but that's fine. You're going to see one in your homework. And then the value of d determines the horizontal translation. So this is pretty much very straightforward. This value of c determines the vertical translation. You've dealt that with grade 10. This should be very straightforward. And that sums up our entire lesson. There is homework on page 35, 36, and 37. I suggest you doing all the odd numbers. That should be it. Okay. Yep, that's it. Have a great day, guys.